So there you go. So for this one, first of all, I want to, apologize for the fact that this is not in a slide form. I would have loved to do that, but we weren't able to do it. Traveling between two contents, French and English, not always easy, but that's not a total excuse. Anyways, can I just confirm that we are here? I have Memos, Akili, Igor, and Maureen. Are we all back? Thumbs up or something. I just want to make sure I'm not talking with myself.
Yes, we are here. We are here.
Okay, great. So let's see. So really, this second part is about introducing us to a very, very important concept, which is the concept of identity. We call it self-sovereign identity. We insist on self and sovereign, which technically can mean the same thing. But that fact that we insisted was, or those who created that was definitely on purpose, because today in the context we live in, we live little drops or crumbs of our identity as we move around, and we don't even really realize it. How many passwords and username do we have in sites? How many information have we created in those multiple sites that we sign in for one time and then we drop out? So this has become a very serious problem in the IT community. And this concept of self-sovereign identity combined with decentralized identities that was enabled by these new technologies is really important. So let's talk a bit about, I'm assuming that most of you went through this document. So I want to make sure that we make this as interactive as possible. So feel free to stop me and ask questions so that we can take some time and discuss them more in depth. So there's a practical session that comes with this that we'll focus on tomorrow, together with exercises, practical exercises on the first part. But here we go. So why do we even think that the internet is missing an identity layer? Back then when internet was created or exposed to the public, because there are those two timelines. The military were really concerned about one thing, and that thing was how could they were more concerned about how they could transfer information from one point to another, aka connect multiple machines. And in that goal or objective, they kind of put aside the identity aspect, which end up making things in such a way that you can be on the internet communicating with something that you have no idea about what it is, because the way things are identified on the internet is through protocols such as TCP and IP addresses, as well as MAC addresses. And the funny thing is that IP protocols can change. So my machine does not always have the same IP protocol. Same for the MAC address. My machine does came with one, but I can also change it as I please. So those are the fundamental reasons why internet is missing an identity layer. Now, the problem has become so serious, you just need to look at data and realize how the way we design digital identification system on the internet has pushed us to function basically with what we call username and passwords. And to date, based on some researches that were done by Kim, um, an average user keeps track of 191 passwords. This might sound like a lot, but if you sit down for a second and think about all the password and username you've created since you started working on the internet, I'm pretty sure getting to that number and even going over is not a big deal, um, especially for those who have access to internet and are on it all the time. So blockchain is definitely a solution to this problem, and specifically decentralized identity and self-sovereign identity. And here we are, talking about like now we have the tools that will allow us to just implement a totally different solution that can bring a proper identity layer to the internet. So again, we talked about some numbers regarding password and username, but more interestingly, we can look into the consequences in terms of finance and how those negative consequences affect the trust in service providers. Um, just alone in 2021, $6 trillion in loss caused by cyber crime. I don't know if you are realizing what $6 trillion is, but it's a gigantic amount of money. More than 90% of US consumers believe they have lost control over their personal information. So the feeling is real. Once you have this password, username spread across, and you literally are dropping little crumbs of your identity everywhere, and you have zero control over it. Thinking here about Facebook, your data is living on your server. All the value information you create is living on the server, and you have to go and supplier, as we say in this context, and beg for them to give you a copy of your data. I mean, some degree you're also consuming their service for free. So that's what it is. And only in 2016 specifically, we had 3 billions of Yahoo accounts hacked. That's incredible. That's what you get when you ask a central authority to manage your password and username. You literally give them control, and given that they are central authority, they can be easily targeted, and we get that. So again, another number that can really get us think is that 63% of network intrusions are the result of compromised user password. So the password username has become a real big issue when it comes down to identity. After all, you provide your username and password because you want to be identified. So again, why do we think that SSI or decentralized identity can finally be the solution? Well, it's because SSI and decentralized identity are first-class security. By first-class security, I mean that the notion of security and the notion of confidentiality, integrity, availability are baked into their protocol. So they are at the base of thinking about this system. So it makes it in such a way that I'm not building internet as it was built and then later thinking about the identity layer. No, I'm thinking about the identity layer as I'm putting my first little piece or block to elevate the foundation of internet. So that's the difference here. That's why we think SSI and DID can finally be the solution, or bring the solution, or sound solution to the problem. The other aspect is that, SSI fundamentally shifts the locus of control, because in identity system today, what we see is a central authority basically having all the control, and the user having basically nothing. So the control is shift. So it's totally a paradigm shift, where instead of having someone else be in full control of your identity, you are in charge of your identity, and the relation with other entities become like, uh, validated, wanted, mutual, and equal. So all those concepts are built into our baked into the founding building block of what SSI is suggesting. So we talked about the locus of control being, uh, mostly in favor of centralized entity authorities such as Facebook, Amazon, any other you can think of, Yahoo, and so on. And you can see here in this picture how the user is literally kicked out on this left picture here. I don't know if I can annotate this. Oh yeah, no. There. I hope you're seeing. So on this left picture here, you can definitely see how here the user is kicked out of the locus of control. The issuer, in this case, Facebook, is again the verifier of your identity. And meanwhile, on the right-hand side here, we see that the user is part of the locus of control. And we have a registry that we all share, and through which we can, confirm, make some assumptions. So that's the difference there. So now I did annotate on my screen. Oh my goodness. How do I remove this? 1 second. Does any of you know how to clean this up? Just 1 second. I want to make sure. Oh, cool. So figure it out. Make sure I don't have the pen. Okay. So next, let's talk a bit about the risk that we have on the internet. So one fundamental risk that we have is called the man in the middle. So basically, as you see in this picture, what happens is someone places himself in between you and what you think you are reaching out to. It could be a web application, it could be Google, it could be Facebook, and then he presents to you something that might look like Facebook sign-in page. Meanwhile, it's his signing page, and as you provide your information, password, username, he grabs it, and then he's able to get into your account with the information you just provided. The replay attack here is simply the idea that we perform transaction on the network, and somehow someone is able to grab the command that you initiated to a system, and then replay it later, because that command come with everything in it, your identity and everything. So if he's able to collect those commands you are initiating through your device, he can then later replay those commands. And Uh, and in this case, you see if it's a bank transaction, look at what could happen here. He can replay that command multiple times and kind of empty your account. There are definitely solutions to this problem as long as you take into consideration. But unfortunately, most systems that we see out there today, especially in our context, are not even aware of this type of attack. So I see a system being implemented with making transaction and not finding a way to identify them in a unique way, in such a way that when the consuming system gets a transaction, and then it can answer the question, is this a transaction that I have gotten in the past? And it's simple. You can just identify it using what is called like a nonce or a unique number in such a way that you can replay, duplicate commands or transaction. So the password attack, that one is obvious. There's guessing the password by running this intensive, memory intensive computer or devices to try all the combination possible.
Please, I have a question.
Yes.
Can you come back to the previous attack?
Yes.
Yes. I want to ask if the the duplicate message is altered.
You want to know if the duplicate message is changed or something like that?
Yes.
Okay.
Mm-hmm.
So usually they don't necessarily change it, although that might be a possibility. But the idea here is really to cause damage to, let's say, Antonio, right? Let's say Antonio is sending 1,000 euro to, no, let's say you and Ted are sending 1,000 euro to, uh, to, um, to me. And then
Mm-hmm.
somehow I'm able to get that request you made from your computer. So I'm somewhat in the middle of your computer and the system that you're using or your bank, right? And I'm able
Yes.
to get that command that you initiated or that request, HTTP request, or that instruction that you gave to the bank application. And then what I can do is replay that same instruction multiple times and empty your account. So I don't necessarily need to modify the message and say, oh, send it to this other person instead. So I can just reuse the exact same command you send and and do that. Does that make sense?
Uh, yes. That means that the message is also duplicate with the time that the message was sent.
Exactly. And that's what is said here that, one way to prevent this kind of attack is just to use timestamp and identify the transaction in a very unique way, right?
Yes.
Uh-huh.
Okay. So. Mm.
That's one way you can do it, or you can use a nonce. Both concept are similar, like they're identical. It's identifying the transaction in a unique way, in such a way that the receiving party, when they get the transaction, they can ask themselves, is this a transaction that I got before? And they just navigate through the system and check if that unique identifier is duplicated, is already present. If it is, they just discard the transaction. If it's not, and then they process the transaction. Is that good?
Yes. Yes. It's good. Thank you.
Okay. Mhm. So password attack, again, it's really about either guessing your password. We're using some random approach would consist of trying multiple different passwords and seeing which one, hoping that one will work. The other aspect of this is a dictionary attack. In a dictionary attack, what happens is there are passwords that are called common password. So instead of just trying all the password possible, random password, which is memory intensive and resource intensive, I can just use a dictionary that are online everywhere of common password and try all of those common password first and see if one of them fits your password. Phishing attack really involves, some sort of uh, social engineering. They end up sending you emails, very nice and attractive emails of something you have won, some possibility of winning something massive. And oftentimes they will appear as if it's your friend or your boss, something like that, that is sending you the email. And once they get the email, when you get the email and you click on it, on the link, what happens is he can get a hold of your computer. And he can literally install malware into your computer. So XSS attack, really, it's again injecting malicious code into the JavaScript code. And this one is more of a technical attack, but overall it's playing with the JavaScript vulnerability to gain access to your server or website, if I can put it that way. And there are many attacks that I think you can, I hope you guys read through it and we'll get a chance to come back to it when we do our practical exercise tomorrow. But for now, I want to move on to the next session, which is the current solution, because I think these are very self-explanatory. Database cracking is pretty much what we talk about. Exploiting software vulnerability. Here we're talking about, writing software in such a way that there's no vulnerability, because the way you write software can, definitely expose you to some of these vulnerabilities. Packet sniffing is really about getting in the middle, in between you and the system you're trying to reach out, and kind of having access to all the information you're sending. SQL injection is really about injecting some code into your queries, into your fields, in such a way that it will execute when you get to your database and cause some damage, serious damage. So the current solution that we observe out there are really centered around cryptography. And cryptography is really about, I would say, encrypting information. And encryption really consists of, I don't want to say hiding, because it's not really hiding. It's changing and restructuring the information in such a way that it's not easily you can read, but you won't have the sense of the original information. So I get encryption. Uh, uh, Another way is a way to scramble the content of a message or a document in such a way that only those who have some sort of secret key or some sort of key can have access to the real original information. So that's the process of encryption. The founding construct in cryptography are hash functions. So hash functions, the encryption process, digital signatures, verifiable data structure, and proofs. And we will get a chance to talk about those more in details. Um, what I want to stress on here is the fact that cryptography is divided into two families. The first family is what we call symmetric key cryptography, and the second one is asymmetric key cryptography. In symmetric key cryptography, we can just focus on this image to explain the concept. What happens is I have two parties. I do have someone on this left hand side willing to send some sort of information. And then on the right hand side over here, let me take my drawer. So over here, I have someone willing to send some sort of information. On this other side, I have someone willing to receive the information. So the sender is sending to a receiver. What happens in symmetric cryptography is a secret key is generated. Look at it as just a key. I produce some content that I want to send to the receiving party. Now, the key that was generated is used to encrypt my content. So when I apply the key to my content, through this process, the encryption server, I get what I call a cipher test, which is basically the encrypted version of my plain text information, message, or whatever I'm sending. And the fact that I'm now sending an encrypted message naturally create a secure channel, as you can see here, of communication that only both of us, me, the sender, and the receiver have access to. And now for the receiver to have access to the original message or the unencrypted message, he has to have this key, the same key I encrypted the message with. He has to have that same key so that he can use it to decrypt the message. And that's the process of symmetric cryptography. And as you can see, it comes with some shortcomings. It being that how do we share this secret key over the internet without the risk of revealing it to other parties? So that's something that is very interesting to look into. So now, moving on to the next type of cryptography, which is asymmetric key cryptography. So again, we still have two parties willing to exchange some sort of information, the sending party and the receiving party. And in the process of exchange, I also want to have, because you are exchanging information, but at the end, you are also validating information, and you're also making sure that, that information was not tampered with. So it's not only the need to exchange for information within a secure channel, but it's also making sure that that information remain valid and the same throughout its journey. So asymmetric key cryptography, here we have two keys. So remember, in the first case, we have only one key, which was called the secret key, and both parties had to have the key. In this one, we have each party, whether that's the sender or the receiver, with two keys, with the particularity that that pair of key is, they have one that is public and another one that is private. So they each have a pair of keys, one public, one private, each of them. Now, the sender, what he does is he can, there are different scenarios. And so I want to make sure that I'm clear here about it. The sender he uses one of his keys to encrypt the message. And once he uses one specific key to encrypt the message, only the other key in the pair can be used to decrypt it. So let's get more specific. So the sender here, if he uses his public key to encrypt the message, only his private key can decrypt the message. Meanwhile, if he uses his private key to encrypt the message, then the message will be decrypted by his public key. So if somehow the receiving party has its public key and he encrypts the message with his private key, and then the receiving party can decrypt the message with his public key. And that's usually what happens. So, the public key, as its name indicates, is public key. So they find a mechanism to exchange public keys as a first step, usually called handshake and all of that. It's a little bit more complicated than that, but in general, the idea is that somehow the receiving party gets a hold of the public key without any risk because it's public. And now this sending party can then, this sending party can encrypt the message he's sending to the receiving party with his private key. And now, since given that the receiving party has the public key, he can decrypt the message sent by the sending party. So as simple as that. So I want to make sure that this concept is clear and crystal before we move forward. So please feel free to ask any question if you have it. Thank you. Okay, so let's continue. So 1 second here. So again, having described what cryptography is, DID makes extensive use of asymmetric key cryptography. So now you understand why DID is special. DID stands for decentralized identity. And it definitely follows the same principle that we just went through here, in a sense that, DID holders store private keys for the DIDs that belong to them in their digital wallet. And public keys for DIDs are made public and discoverable. So that's how it basically works. And for those who are curious, this is more of a research thing. That's the structure of a decentralized identity. That's how it is. The public key part look like this. The private key part looks like that, and the DID itself looks like that, with each of these, part, specifying, respecting the specification that I invite you to look into. That's a little bit outside of the scope of this presentation. So now we talked about encrypting and all of that, but what is it really? This is done through hash functions. Hash functions are basically functions that you pass some sort of input through, and at the other end you get a message of a fixed length. So every document that you pass through a hash functions will produce, no matter how long it is or how short it is, it will produce a fixed size characters at the exit. And what's good about hash functions is that you provide the same input. At the exit, you have the same hash or a set of fixed characters. And again, the purpose of hashing here is really to, again, encode or kind of obfuscate or hide the content, or in other words, is to provide a resume to a message, and also making sure that you can tamper with, because if the input changes even a tiny bit, and then the hash you obtain becomes incredibly different from what it was previously. So of course, there are different type of hashing functions, and this is more of inviting you to look into them. But what we have retained here are those. We do have MD5 and also SHA-256. I just want to mention that some of these are really not recommended, like MD5. It's pretty old and kind of outdated. It's still in use, but we definitely don't recommend that. SHA-256 is a pretty good one, and all they have common characteristic, which are really center around the efficiency, their resistance to pre-image, and their resistance to second pre-image or collision. We'll talk more about that later. So again, hash functions are used in self-sovereign identity and decentralized identity as a building block for verifiable data structure. Just like we mentioned earlier, cryptography allows us to verify structures, and hash functions, which are definitely a core element in that, help us do just that with SSI. Digital signatures just refer to the concept of signing something and saying it's me, and then later this could be verified that it's basically actually you who signed that. And if you remember the concept of public and private key that we just went through, it's just talking about digital signature in some way, in the sense that if you can encrypt a message with your private key and send it to me, and I can decrypt you with your public key, and then I can be sure that it's definitely you who sent that message or who signed that message. So again, digital signatures, as I mentioned, rely on public key cryptography, and public key cryptography is another name for asymmetric cryptography. So you need to write that down. Public key cryptography is another name or another way to call asymmetric cryptography. Meanwhile, private key cryptography is another way to call symmetric cryptography. So still on the current solutions, we have HTTPS, which is the protocol through which we send data over the web. I think you're all familiar with this, the HTTPS that you see in your browser, as opposed to HTTP, which is just plain text. HTTPS encrypt data before sending it through the network. eSpec is simply a group of protocol used to establish encrypted connection between devices in a generic sense. So what I want to point out is that all these current solutions, although they seems to use cryptography, because we talked about HTTPS and we talked about the fact that symmetric and asymmetric cryptography are used extensively in the current solutions that are offered today for the question of identity. The problem remains that these notions are not integrated from the start of building information systems. So they kind of come later as an add-on, as a plugin, and that's the very dangerous aspect of things, and it makes it in such a way that SSI and DID place themselves well to suggest something different, which is really baking this notion of cryptography and hashing into the basic building block of a different architecture. After all, good design is good security, and good security is simply good design. So, how does identity work on the internet today? After all, what is identity? There are many ways we can define identities. So I just want to point out some the most prevalent or interesting ways we can look at identity, because you get into different contexts and it means different things. So this concept of electronic identity, and some government issues electronic identities to their citizen, even for online use. And the next one is attribute-based identities. Someone who is older, 18 years, at least 18 years older, that's an attribute, and that's a way to also identify someone. And in this specific one, when kids go to buy some products like alcoholic or cigarettes in some countries, you are required to show your identity, and you must be at least 21. That's an attribute, what we call an attribute-based identity. Okay, so now we are at 6, which is when we should stop. So I just want to check with you if it's fine to just finish this introduction to identity, so that tomorrow when we meet, we can just run through all of this and finish it. But I think it's fine if you guys are feeling like already tired. We can just continue tomorrow. That's definitely fine. But before we stop, I would say if there are any questions, please feel free to ask. If there are any comment to today our session, feel free to just unmute yourself and talk. Because at this point, I think I might be calling on people. Let me make sure I stop the recording.